Hi everyone. So today I want to talk about coloring 101, which is also known as Ramsey theory. And I did this topic for my DRP this summer, and I thought it's pretty interesting. So I hope some of you guys enjoyed this presentation. So first, we're going to start off with an example to sort of motivate our definition of Ramsey numbers. So our example is that among any group of 6 people, it's guaranteed that at least 3 people mutually know each other, or at least 3 are strangers. And this is regardless of which 6 people you pick. Um, this is guaranteed to hold. So first, I want to clarify that knowing in this case is a symmetric relation. So if A knows B, then B will also know A. But it's not transitive, which means that A knowing B and B knowing C doesn't mean that A knows C. So with these two restrictions in mind, uh, you can imagine that we can actually turn this into a graph where the nodes are the people, and then the color of the edge is represents either them knowing or not knowing each other. So let's say, for example, red means you know the person or the 2 people know each other, and then blue is the opposite. So they don't know each other. And then, so what I'm claiming in this example is that either you have a red triangle or a blue triangle, because the triangles are groups of 3, and then red triangle means they all know each other, and blue means that they all don't know each other. And so let's see why this is true. So we're going to call the people A through F, as you can see in this diagram, and we're going to focus on A's relationship to the other 5. So since there's 5 people, we can split them into 2 groups, a group of people that know A and a group of people who don't know A. And now one of these groups has to have at least or size of at least 3, because if they were both size 2, well, 2 plus 2 is 4, which is less than 5. So one of the groups has to be at least 3 people. And let's say, without loss of generality, that it's red. So there's at least 3 people who know A. And so let's say that these people are B, C, and D, as I've outlined in red here. Now, if any pair of these people know each other, let's say B and C know each other, then that means A, B, and C are going to form a red triangle, which was what we wanted. So B and C can't know each other, and then similarly, C and D can't know each other, and B and D also cannot know each other. So we draw blue edges between all 3 of them. But now we've just formed a blue triangle. Well, I guess in this case, it doesn't really look like a triangle because of how I've drawn the edges. But they're a group of 3 people who all don't know each other, which is the other condition that we wanted in the example. So that proves the case of at least 3 people knowing each other. And for the case of at least 3 not knowing, you can apply the exact same logic and you get the same thing. So in either case, we've guaranteed the existence of these monochromatic triangles. And so now that brings us to our definition of Ramsey numbers. So the definition is R of AB, where R stands for Ramsey. It's the least integer n, such that when you color the edges of Kn is a complete graph of n vertices. If you color the edges of Kn red and blue, then there must exist either a red clique of size A or a blue clique of size B. And here a clique just means a monochromatic subgraph. So for example, the red triangles are red 3 cliques, and the blue triangles are blue 3 cliques. And if you also want to think of this Ramsey number definition in terms of the language of the example, R of AB is also the least n, such that among any group of n people, there's a group of A mutual friends or B mutual strangers. And so with this casework that we did earlier, we've just proved that R of 3 is at most 6, because we've shown that there has to be, um, if we take 6, then there guarantees the existence of this triangle. But it might also be the case that it works for 5 or 4. But so we need to bound it the other way in order to actually figure out that R of 3 is equal to 6. And the way that we prove upper bounds, R of 3 is greater than or equal to 6, is we need to construct a counterexample for 5. That is, we need to find a group of 5 people with some relation of knowing or not knowing each other, such that we avoid these monochromatic triangles. And it turns out that I've prepared this group of 5 here, and you can check that there's no triangles in this graph. So we do indeed have that R of 3 is greater than or equal to 6, which implies that R of 3 is equal to 6 because we've established both bounds. So yeah, that's cool. We've shown that R of AB is 6 when A and B are both 3, but we don't actually know yet that R of AB exists for all A and B. But that's actually what Ramsey proved about 100 years ago. And the way he did it was you use induction, and once you've proved the base case, if you want to find R of A and B, it turns out that R of A and B is bounded above by this number. And sorry for my poor handwriting, but yeah, it's bounded above by R of A minus 1B plus R of A and B minus 1. And the proof of this claim is actually using the exact same logic as we did in the 6th example. And I invite you to try it yourself if you're interested. So anyway, now that we know that Ramsey numbers exist, do we know their actual like exact values? It turns out we basically don't for almost all n. Well, we know 3 and 4. We showed in the example earlier that 3 and 3 is 6, and R of 4 and 4 turns out to be 18. But 5 and 6 are still open problems. And to see why, well, if you consider, for example, let's say you want to establish a lower bound on Ramsey of n and n. Well, then you would need to check all colorings of Kn, and for each coloring, you need to check that it avoids the K click, or you need to check that it avoids. Sorry, this should be let's use K here. So to lower bound R of KK, we need to, for each n, we need to check Kn, all of the colorings of Kn, and see if it avoids K clicks. But how many colorings of Kn are there? Well, there's n choose 2 edges in Kn. So, and if we color each one either red or blue, there's 2 to the n choose 2 colorings, which grows on the order of 2 to the n square. And that's extremely computationally difficult to work with. Computationally difficult to work with. So yeah, we basically still don't have a way to figure out the exact values except for very small k. And to give you an idea of how difficult this is, Erdős basically believes that if aliens threaten to invade us, unless we got the Ramsey number for 6 and 6, then our best course of action would basically be to attack them first. And I think that's kind of a funny quote. But yeah, so if we don't know the exact value of Ramsey numbers, then what do we actually know about them? Well, speaking of Erdős, it turns out that he actually came up with a clever method to show that the Ramsey numbers grow at least exponentially. So the way he did this was, if you fix an integer n, and you take the complete graph Kn, and you randomly color it, and then you compute the expected value of the number of K clicks across all of the random colorings, then you will get some expression in terms of n. And then if you choose n such that this expected value is less than 1, well, the expected value is just the average across all of the random colorings. So if the expected value is less than 1, there has to be some coloring with 0 k-clicks. That means that the Ramsey number is at least n for small enough n that satisfies e is less than 1. So we want to satisfy this inequality. And let's first figure out what is e. So notice that if you fix k and n, there's n choose k different k-clicks in the complete graph. And now, if we focus on one singular k-click, what's the probability that it's entirely red? So that would, well, there's inside of each click, there's k choose 2 edges. So for it to be entirely red, if we color it randomly, there's a 1/2 chance of red and 1/2 chance of blue. That means that the probability is 1 over 2 to the k choose 2. Similarly, for blue, there's also 1 over 2 to the k choose 2 probability of it being all blue. So in total, the probability of it being monochromatic is 2 to the k choose 2 minus 1. Or we're going to actually write this as 2 to the 1 minus k choose 2, just for convenience. So there's n choose k different k subgraph, and each subgraph has a 2 to the 1 minus k choose 2 chance of being a click, a monochromatic click, which means that the expected number of clicks is just n choose k times 2 to the 1 minus k choose 2. And now we want this number to be small. In particular, we want it to be less than 1. So how do we make that possible? Well, if we rearrange the equation, sorry, my handwriting is not very good, but we get n choose k is less than 2 to the k choose 2 minus 1. And then now we're going to use the fact that n choose k is less than or equal to n to the k. So if we can make n to the k less than this expression, then that's sufficient. So we have n to the k is less than 2 to the k choose 2 minus 1, which means that any choice of n which satisfies this inequality will work. And so how does this bound grow? Well, recall that k choose 2 is equal to k times k minus 1 over 2. And then that grows about as large as k squared over 2. So that means that this bound is approximately 2 to the k squared over 2. Sorry, that's not a good 2. All to the 1 over k, which is equal to 2 to the k over 2. So we've just shown that the bound for our Ramsey number is 2 to the k over 2. So r of k and k is greater than 2 to the k over 2, which means that the Ramsey numbers must grow at least exponentially. So now that we've finished our discussion on Ramsey numbers, I want to go over a few other Ramsey-like theorems. And at first you might be wondering why they're all under this classification of Ramsey-like theorems, because they will seemingly have nothing to do with each other. But it turns out that they are actually related in interesting ways, which I'll talk about later. So the first one I want to talk about is van der Waals' theorem, which says that if the positive integers are r-colored, then there exists arbitrarily long monochromatic arithmetic progressions. So let me break down what this means. So first of all, you have the positive integers, 1, 2, 3, 4, and so on. And R coloring just means you have a finite number of colors and you have R of them. So if R is equal to 3, your colors might be red, blue, and green. And then an R coloring of the integers just means for each integer you assign it a color. And this can be in any way you'd like. So let's say we have red, green, blue, and then let's say I want 4 to be red as well. That would be, if you continue this on indefinitely, that would be an example of an R coloring of the positive integers. So now what the theorem is saying is, let's say my friend, he asks me, does there exist an arithmetic progression of length 10? And then if this theorem is true, then that means I can say, oh yeah, for example, there's 10 red, take these 10 red numbers, they're actually forming an arithmetic progression. And then if he asks for like 12, then I could say, take these 12 blue numbers, and I get an arithmetic progression out of those. And no matter what length progression my friend asks me for, I can always find a color and some numbers in that which are colored that way, such that they form an arithmetic progression. So that's pretty neat. And I'd also like to talk about a few other results of the same flavor. So the first one's by Semiretti in 1975, which says that if A is a subset of the positive integers with positive density, then A contains arbitrarily long arithmetic progressions. So note that this actually directly implies van der Waals theorem. It's a stronger statement because, well, if you have a finite number of colors, then and you partition the positive integers into these finite classes, then at least into the finite number of classes, then at least one of the classes has to be infinite. But I guess other examples of positive density, you might be wondering what positive density means. Another example of a set with positive density would be the even numbers, because they have a density of 1/2. Every other integer is even, roughly speaking. And then, but this theorem doesn't say anything about the prime numbers, because the prime numbers, their density is about 1 over log n. So they'll grow sparser and sparser over time, which means that they in fact have a density of 0. So Semiretti's theorem can't say anything about the prime numbers. But it turns out that even though the prime numbers have a density 0, they still have this nice property of having arbitrarily long arithmetic progressions. And this was proven by Green and Tao in 2004. And by the way, Tao here is actually the famous Terence Tao that you all know. So next up, I want to talk about tic-tac-toe. Well, this theorem is actually not exactly about tic-tac-toe. It's called the Hales-Jewett theorem. It talks about hypercubes and combinatorial lines. But in order to understand like the formal statement with the combinatorial lines and hypercubes, you need to understand a bit of like technical definitions that I don't feel like talking about here. So I'd like to instead talk about this theorem in terms of tic-tac-toe. So let's say you give me two numbers, r and n, and we have r players which are playing tic-tac-toe on a grid of side length n. So if you take your traditional game of tic-tac-toe that we all know and love, that would be the case r is equal to 2 and n is equal to 3 because, well, there's two players playing tic-tac-toe and your board, well, the length is 1, 2, 3, like so. So if you make the dimension of the game sufficiently large, then a tie is impossible. That's what the theorem is saying. So turns out like the game that we've all played before, tic-tac-toe, it's played in 2 dimensions, right? And you'll know that if you play 2-dimensional tic-tac-toe, it's definitely possible to make a tie. In fact, if both players know what they're doing, you'll almost always end up with a tie. But what Hales-Jewett says is that if you instead play this game in a high enough dimension, you can make the dimension large enough such that a tie is impossible. And a nice corollary to this theorem is that if a tie is impossible, then that means that the first player actually always has a winning strategy. And this uses a little bit of game theory, and I'll let you think about why that's true. So the next topic I want to talk about is monochromatic solutions to systems of equations over the integers. So there's this nice result from Schur in 1916, which says that if the positive integers are r-colored and you can recall the definition of R coloring. It's assigning color to each integer, just like we did in van der Waals. But if the positive integers are R colored, then there exists a monochromatic solution to x plus y equals z. So what that means is that if you R color the positive integers in any way you'd like, then you can always find a triple x, y, and z such that they're all the same color and they satisfy x plus y is equal to z. And this is actually one of the nicer applications of Ramsey numbers. So it turns out that they are in fact pretty useful. And this theorem, if you use this result along with a little bit of group theory, then it allows you to prove this interesting theorem, which looks a little bit like a counterexample to Fermat's last theorem. So for all integer powers m, if p is prime and sufficiently large, then this equation has a non-trivial solution into integers mod p. And some of you might recognize that this x to the m plus y to the m equals z to the m is actually the exact same equation that appears in Fermat's last theorem, except Fermat's last theorem says something a lot stronger because you don't have this modulo p caveat. And by the way, here non-trivial just means you can't do something silly like plugging in all 0 and you get 0 is equal to 0 as a solution. So the last thing I want to talk about is subsequences of distinct real numbers. So here's a question for you. What's the least n such that any sequence of n distinct real numbers contains a monotone increasing subsequence of linked A or a monotone decreasing subsequence of linked B? Okay, so this is a little bit of a mouthful. So let's sort of unpack what that means. So let's say we have a sequence of real numbers. So they could be like 1, 2, 1/2, 3, 1/3, 4. So in this case, 1, 2, 3, 4 would be a monotone increasing subsequence. And then, for example, 1, 1/2, and 1/3 would be a monotone decreasing subsequence. And we're asking what's the least n such that, given A and B, what's the least n such that either one of these subsequences is guaranteed to exist. So the immediate bound, the one that might come to mind first, is that n is less than or equal to r of AB. And the reason why this is true is because let's say we have a sequence AI of distinct real numbers. Well, and let's say that we have n of these. Or let's say we have r of AB of these, sorry. So let's say we have r of AB of these. Now, what we do is we construct a complete graph, KR, and we color the edges of the graph like so. We take the ordered pair IJ, where I is less than j, and then we color IJ by red if AJ is greater than AI, and then blue if the other case occurs, so AJ is less than AI. And note that this is well defined because we can't have equality since we've said in the problem statement that the numbers have to be distinct. So now, by the definition of R of AB, there's either a monochromatic red A click or a blue B click. So if there's a red A click, you have A numbers such that this condition holds, which means that they form a monotone increasing subsequence. And then in the other case, if you have a blue B click, then you found a monotone decreasing subsequence of linked B. So that shows that this bound does indeed hold. But we can actually do much better than that because remember that R of AB is exponential in A and B. We showed that in the earlier section about the exact values of Ramsey numbers, or not the exact values section, the Erdős probabilistic method section. My bad. But we can actually do much better. We can get a bound on the order of A times B. And that bound is actually going to be a minus 1 times b minus 1 plus 1. And sorry, let me move this out of the way. So one thing you'll notice is that there's no more inequality sign here, which means that we actually have both directions. And what does that mean? That means that we can actually find a counterexample when n is equal to this number, a minus 1 times b minus 1. So there exists a sequence of a minus 1 times b minus 1 distinct real numbers where it avoids both the increasing and decreasing subsequences. And actually, my mentor and I constructed this sequence together, but I don't really remember how the construction went. So you'll just have to figure that out on your own if you're interested. Sorry. But yeah, so anyway, back on topic. So the proof of this result is actually very reminiscent of dynamic programming. So what you do is, let's say we have a sequence of n distinct real numbers where n was this number that we wrote up here. So we call the sequence ai, and for each I, we label ai with the ordered pair xi, comma, yi. And then we're going to define xi and yi as follows. So xi is the length of the longest increasing subsequence ending at ai, and yi is the same but for decreasing subsequence. So if we go back to our example here, we have, let's look at I is equal to 4, the fourth number in the sequence. And so we have ai is equal to 3. Well, you'll observe that the longest increasing subsequence is 1, 2, 3. Well, that is the longest increasing subsequence ending at 3. So that means that xi is equal to 3. And now what's the longest decreasing subsequence ending at 3? Well, all of the numbers coming before 3 are less than 3. So the only way we can have a decreasing subsequence is if we just only take 3 by itself. So I should write 4 here. x4 is equal to 3 and y4 is equal to 1. So now what I claim is that if you label each index I in this way, then you can never repeat labels. That is, like, if you take two indices which are different, then either their x's are different or their y is different. They can't both be the same. And to see why this is true, let's say we have I less than j be two indices. If aj is greater than ai, then that means that xj is at least xi plus 1, because you can just take the longest subsequence ending in ai and then append aj to the end of it, and you get another longer increasing subsequence that's linked one more. And then similarly, in the other case, aj is less than ai, then we get yj is at least yi plus 1. So now we've shown that they actually can't have, all the labels have to be distinct. And now what I claim is that xi and yi cannot be bounded like this. So suppose they were, so basically there has to be at least one index where x escapes this bound, says xi is at least a, or yi is at least b. The labels can't all be bounded in this manner. And to see why, well, let's look at what we chose for the value of n. If assuming that x and y follow these bounds, there's a minus 1 times b minus 1 different labels. And we know that every index is going to have a different label by our uniqueness claim. So, but there's a minus 1 times b minus 1 plus 1 different indices, which means that two indices have to have the same label, assuming that these bounds hold. But that's a contradiction. So either we have an index of x that escapes this bound, or we have y escaping this bound somewhere. And then if x escapes this bound, then we found an in a monotone increasing subsequence of length at least a, and if y escapes this bound, we found the same but for a decreasing subsequence, and that completes the proof. So now that we've talked about all of these different theorems, you might be thinking that they sort of don't really have anything to do with each other. For example, Hales-Jewett was about like tic-tac-toe, and van der Waals was about arithmetic progressions, and then Schur's theorem was about like systems of equations. They're all sort of unrelated to each other. But the reason why we classify all of these theorems as under the name of Ramsey theory is because they're all about inducing an orderly substructure within a chaotic structure. So the chaotic structure is like the R colorings, because the R colorings, all of the theorems are sort of independent of like a specific coloring. They're saying no matter how you color the structure, there's going to be this orderly substructure. Like van der Waals, for example, no matter how you color the positive integers, there's going to be a monochromatic progression. And then, so yeah, they're all about taking this chaotic structure, and then you have some sort of nice substructure within them. So for van der Waals, that was the arithmetic progressions. For Hales-Jewett, that was the combinatorial lines, and so on and so forth. So another interesting thing is that van der Waals and Hales-Jewett actually have a very direct relation between them, because it turns out if you take a combinatorial line and you take all of the coordinates and then you apply, you have a map that sends the coordinates to sort of like a base K representation, then if you apply this map to the entire line, you'll get an arithmetic progression, which means that there's an injective correspondence from combinatorial lines to progressions. And you can use this fact to actually prove van der Waals theorem using Hales-Jewett theorem. So it turns out that there's actually an interesting connection between these two. And so that's the end of my talk. And I didn't go into detail about van der Waals and Hales-Jewett theorem because the proofs is actually pretty technical for those two theorems. But I guess if any of you guys are interested, then I could also make a video about that. So just let me know, I guess. But yeah, I hope you guys thought this is interesting.